Okay, now is a good time. We shall get started. Hello, everybody. Welcome to the Trustworthy Machine Learning Young Scientist Seminar. This is JianFu. I'm a visiting scientist at Recon AIP. Today, I'm going to host today's TrustML YSS. First, let us introduce our first speaker, Thanh. He is a postdoctoral researcher at the Department of Computer Science, Johns Hopkins University. His research focuses on characterizing the statistical and computational aspects of machine learning, with the main topics including reinforcement learning, robust machine learning, and transfer learning. He finished his PhD at Deakin University, Australia in 2022. Today, let us hugely welcome Thanh to give us his talk on the theory of offline reinforcement learning, data diversity, posterior sampling, and beyond. Hi, Thanh, please get started.
Thank you for the introduction, Thanh, and hi, everyone. So let's get started on this. So I'm from Johns Hopkins, and I'm very happy to join our seminar today and give a talk on our recent work on offline reinforcement learning. So as we know, so reinforcement learning is like ubiquitous in many practical setting problems, ranging from like finance to self-driving cars, game playing, networking, and autonomous driving. So the basic setting in this successive reinforcement learning is that the learner needs to interact with the environment. But what if the interaction with the environment is expensive? So this happens in many high-stakes application domains like self-driving cars, financial investment, or clinical diagnosis. For example, we cannot just explore the treatment on a real patient because it can be very risky and unethical. So that leads to the question is, can we leverage the historical interaction data set to learn some optimal behavior from the data sets? And this question is very meaningful in two aspects. First, not just because that the online interaction in practice sometimes very costly, but also because we have the huge amount of usually have like plenty of like historical data set available in many settings. So in offline reinforcement learning, we will like learn some optimal policy from the data sets, the historical data set, and then we deploy that policy in some new scenario. And the key challenges in offline reinforcement learning is distribution shift, because basically the distribution of the offline data is different from the data distribution induced by the target policy that we want to learn about. And also another challenge is generalization. So we only learn from limited pre-existing offline data. So how can we generalize from the scenarios seen in the data set to the new scenarios in the last state space? And another important issue is about efficiency. So can we design the statistical efficient and oracle efficient algorithms to do the offline reinforcement learning? So let's get a little bit more on concrete setting of the offline reinforcement learning. Say here in this work, we will consider episodic time inhomogeneous mock copy system process. So the environment is defined by state space S, action space A, capital H is the horizon, the length of the game, and some initial distribution. So when an agent playing on that MVP, an agent it have specified policy pi. So basically, the agent will get one trajectory for one episode, ranging from S1 A1 R1 to S8 AH R8, and it's followed from a transition of PH and the reward of the MVP. And in this work, for simplicity, we assume that the total rewards are bounded by some quantity, let's say constant B. And the setting in offline reinforcement learning is basically now we don't have the interaction with the environment. Then the learner is given some kind of data set, let's say D. So D consists of K is the number of episodes that the agent have in the historical data, and each episode is basically the whole trajectory from time 1 to time capital H. And in this setting, in this problem, it comes to a very general setting where the behavior, the data, the offline data, the offline policy that collect the offline data is called mu for behavior policy. This can be adaptive. This means that it can change over a different episode. And the goal of offline reinforcement learning formally is to design a learning algorithm from the offline data set such that we can extract a policy that this can compete with any comparative policy pi. Okay, so this learning objective defined by suboptimality. So it's basically the value gap between the comparative policy pi and the policy pi hat. And here's some notation. So we will denote mu t for the behavior distribution at the episode t, and we denote mu is just the average of all the behavior policies. So that's the basic settings of offline reinforcement learning. So if any have any questions, so please just stop me to clarify this. So let's say now I will go into some the key research question and some prior works in this papers. So offline reinforcement learning. So as I mentioned, one essential problem of offline reinforcement learning is to deal with the distribution shift. And to deal with that, so basically, prior works need to kind of quantify the measure, some kind of the decrease of distribution shift in the offline data. So the early works of offline reinforcement learning, they use like uniform concentratability coefficients. So basically, they assume that the offline data has a uniform coverage over all the states and action pairs. So that's why it's possible to learn the optimal policy from just offline data. But that kind of assumption is very strong and it doesn't hold in practice. So lately, people like the majority of methods focus on something called pessimism principle. Roughly speaking, pessimism principle is like how to extract from the offline data. When we extract from offline data, we take the decision on the basis of the worst case scenarios. So based on that, many new data coverage notions are proposed, like single policy concentration coefficient, relative condition number, Bellman ratio. And also on top of that, many algorithms are proposed, like the dominance one in lower confidence bound, LCB, version space algorithm. But they quickly become inefficient in general function approximation when space is large. So question we asked is, what minimal condition that enable sample efficient offline reinforcement learning? And can we design Oracle efficient algorithms with comparative guarantees? So that's quite a question that we try to look into. So to summarize the key contributions here in this talk, in the talk is like two key contributions. The first is we propose a new notion of data diversity. So basically, it's measured generalize the data coverage. And also, we provide a unified result that show that we can go based on version-based algorithms to obtain Oracle efficient algorithms using like regularized optimization and Gaussian sample. I will go more detail on each of this one by one. So for the first contribution about data diversity, so basically this is a notion that is inspired by transform learning. And we use that, we propose a notion for offline reinforcement learning. And the implication of this is that it states the scenarios in which offline reinforcement learning is sample efficient. And so to talk about the second contribution, so let me first mention about one of the beautiful and very important prior work is of the CN co-authors. And this idea is about called Bellman consistent pessimism. So the idea of Bellman consistent pessimism is that it sets up like calculating some kind of point-wise lower bound confidence for the value function to attack the offline reinforcement learning. They propose that, okay, we will construct the version space. So that version space is basically construct the set of all functions such that it has small mailman error in the offline data. And then they take the initial pessimistic estimation of the value function over all the version space, and then they take the greedy action, the optimal action out of that pessimistic evaluation. So we will come more about this idea later in the later slide. So basically, the result from this is that they show that kind of consistent pessimism. The sub optimality, the scale with the standard rate, 1 over square k. So let's just recall that k is number of episode in the offline data, it's like number of sample, effectively. And also scale with some kind of like model complexity and some kind of measure of data coverage. One issue of this thing is that basically that's the version space algorithm. So it's required the optimization, that it requires a constraint optimization over the version space. And this kind of constraint optimization basically in general is not tractable. So later on, they propose some relaxed version of the version space algorithm for regularized optimization. And the idea is basically they induce the regularization term, so increase pessimism, and then to perform the unconstrained optimization. But the thing here is that even if this problem is more practical, the learning rate is much slower. Okay, so 1 over k to the power of 1/3 was much slower than the standard rate of 1 over square root k. So regarding posterior sampling, so posterior sampling is the idea that we replace the optimization by some kind of sampling. And why sampling? Because sampling in practice can be amenable to various efficient approximation like line dynamics. There's a lot of works on this type of direction. And also, however, the posterior sampling is widely used in online reinforcement learning, but not so much in offline reinforcement. One of the reasons is because the sampling is usually associated with exploration. But in offline reinforcement, there's no exploration problem in offline reinforcement. And there's a work by Masatoshi and Nguyen-Tang on posterior sampling for offline reinforcement, but they do on model-based, and they do Bayesian regret. So model-based is not scale in practice. Bayesian regrets have some limitation because it needs some realizability in the prior, and the Bayesian regret is like always smaller than the worst case regret, which we study in this work. So basically, the main message in this work is that regularized optimization and posterior sampling works for offline reinforcement, and they perform just as well as the version space algorithms. So that's the main message of this paper. Okay, so with that highlight of the key result in here, so I'm gonna go a little bit in more detail about the algorithm and the result that we just presented. So the algorithm framework that we achieved such result is basically our key motivation from the Andre Zennes paper and Crystal Dan paper. So in some extent, you can think of our algorithmic framework as a generalization of the arithmetic framework in the Andre Zennes paper to a general function approximation. And our pessimistic posterior sampling builds upon some common Christian there. So, but let's go right into it. So here in the setting here is that we consider function approximation for the value function. And let's say the function class here is some function f, and which is have the Cartesian structures over the time step from 1 to h, because we consider time inhomogeneous MDP. And let's say it's bounded in B. And the function class can be a finite function class, linear function class, or neural networks as done in practice. So the generic offline, the generic algorithmic framework is unified in this one. So that's something we call generic offline policy optimization, or just GOPO for short. This algorithmic is nothing but actually the actor-critic. It's very similar to actor-critic framework. So if we look at the line number 4, line number 4 is, say, given a policy pi t, which is the current actor. So line number 4 will try to estimate the value of that policy pi t, but it tries to compute the pessimistic value. Okay, so instead of just estimate the value, it estimates some pessimistic value of the current actor. And line number 5 is the way we update the actor. So the actor for policy improvement, and I just use very standard update using like the multiplicative weight algorithm for policy improvement. And then we go around for several t iteration, and then we get a policy pi t for its iteration and take the uniform of it and get the output. Now the difference is on how we compute the critic, line number 4. So now in the following, I will present 3 different ways we can implement the critic compute module in 3 different ways. So the critic compute module can use like version space critic, regularization optimization critic, positive sampling critic. Okay. So for the version space critic, basically given the current this is a typo, given the current actor pi t, okay, so we construct the version space f that's consistent of offline data. So the version space is basically nothing but the function, the sets of functions such that the minimax Bellman errors under the offline data is small. So that what it means by consistent with the offline data. And then in the second line, we take the minimization over all the function in the version space f, such that the one would have the smallest initial value. So here we only take the minimize with respect to initial value of the function. And the idea is that we try to encourage the pessimism into the value function in the first time step. Okay, and then we output the value function. So that tends to be the pessimistic value estimate of the current actor pi t. That's the model for version space critic. For regularized optimization, we can do similar things, but instead of doing the constraint optimization, we instead first so the last function we have 2 terms. So the second term is basically just a standard minimax Bellman errors in the offline data. But what important here is the first term is a regularization. So the regularization here encourages to the function to have the small value in the initial state as well. So that tries to encode the pessimism in this initial state. And an important thing to notice here also is that the minimization is the unconstrained minimization. So it's in practice things easier than the constrained minimization over the version space. And indeed, in practice, there's some paper they already have some practical algorithm that of this version that works great in practice, very competitive in practice. And the third algorithm is pessimistic positive sampling. So what we do here, basically, we construct try to be the positive distribution over the offline data. So let's previously see that here is the positive in line number 1 here. So this is the positive distribution. Let me just decompose into important terms here. The second term is basically compute the likelihood, and the role of this likelihood is when we sample from positive distribution, we encourage the function that have small Bellman errors in the offline data. That's the role of likelihood. But what's crucial in this algorithm and make it closable offline policy is the new component, the first term, the pessimistic prior. The pessimistic prior here is basically just exponential of minus gamma, minus lambda time f, the initial value function at the initial, the value function at the initial state of the current active item. So it's the pessimistic prior basically encourage the function that sample from that particular to have small value in the initial state. So in fact, implicitly we enforce pessimism through the sampling by design this by design this kind of posterior with the pessimistic posterior prior. So so that's basically the unified algorithm frameworks that we presented. Okay. So it might come some dance here, but before I move into some main results, so if there are any question about the algorithm, I'm happy to clarify it before we move on to the next section. All right. So it's not question now. So let me try it. So now go to the main result this one. Okay. So given we are representing the main algorithmic frameworks of our work. So let's go into the main result here. So now we will talk about in more details about the data diversity in the paper. Let's first talk about this concept first. What we call is the chi value. Okay, so it's trying to measure the extrapolation from one distribution to another under some business function class. Because offline reinforcement require extrapolation from one data distribution to another. So in order to measure the extrapolation from one distribution P to another distribution Q in the sum function class, let's say capital Q, then we define the chi value. Chi value basically is say that how much the errors, the prediction error under the distribution P can imply about the prediction error under the distribution Q. And for example, let's take a concrete example when P equals to Q. So it means that effectively there's no distribution shift happens here. Then the chi value is cannot basically smaller than one. Smaller than one in the special case when P and Q is equal. Now using that definition, now we officially formally define the notion of data diversity in MPP. So that's one of the contributions. Basically, because the offline learner does not have direct access to the directory of the comparator policy pipe, so they only observe partial information about the goodness of that policy channeled through the transferability of the behavior. So chi value can quantify this. So basically here in this definition, data diversity is quantified by C pi epsilon. Pi is the comparator policy. Epsilon adaptive extrapolation error. So this data diversity is nothing but just the chi value applied on the state's action distribution and under the offline data to the states and action distribution under the comparator policy. So here is the definition of state action distribution. It's basically the probability of reaching that state's and action pairs under the given policy. And the witness function class that we consider here is the mean cos key difference between the function class that we employ and itself. Okay, so at the okay, so that's the definition of data diversity. So despite being that abstraction, then data diversity is always abounded by the common notions of distribution data coverage in the literature, like single policy concentration coefficient, relative condition numbers, and so on. And one important property of the data diversity is it's not increasing with epsilon. It's an easy but also nice property. So let's take a concrete example when the function class is linear with some non-feature phi in d dimension. And then a data diversity of pi with epsilon is always smaller than data diversity of c of pi of 0, which is smaller than this term. Okay, and this term is basically the relative condition number, the term that do the measure the distribution shift between pi and mu, that widely used in the literature of offline reinforcement in the linear setting. So with that definition of data diversity, so this element theorem informally stated, and this theorem is basically say that under a standard assumptions of function approximation, which is to be specific, realizability, and Bellman completeness. Okay. Then three algorithms: version space, regularized optimization, and process sampling for offline reinforcement in the algorithmic framework that we presented. They achieve a comparable. They can achieve a comparable bounds in the sub-value optimality. Here is the bound. So here, basically, they scale with the standard raise 1 over square root k. So just recall k is number of episodes in the offline data. Like model complexity, h is the horizon of the MPP, and c pi k minus 1 is our data diversity. And just one note is that in the positive sampling case here, the bound is the worst case bound. It's not Bayesian bound, so it's stronger than the Bayesian bound. The worst case bound implies the Bayesian bound. So to make it more concrete and put position it in the literature, so let's just instantiate our result to the finite function classes. Okay, so in this table, the gray cells are the new result, our new result. Okay, and we compare with here and the model-based posterior sampling. And the sample point I would like to notice here is that first, in the like regularized optimization is here paper. So they show the unfavorable sample complexity of regularized optimization. Basically, so that they suffer much slower rate, k 1 over k to 1/3. However, we show that it's actually the standard rate. Okay. Regularized optimization can achieve standard rate. And second, the positive sampling here we can show that it does not only work for offline reinforcement, but it's also perform as well as the version space algorithm. Okay, and the third remark here is when we measure distribution shift, so actually the data diversity notion here is tighter than the one like this data coverage notion in the prior. And also a side note of this is that our result holds in the general setting of data collection. So you can see A and I here. So I basically means the episode collected independently. That's the assumption that the frameworks make. In our work, we make the general assumption. So the episode can be collected adaptively, means that the behavior policy can be adapted to its past data. So we further initialize to the linear function classes because in linear case there's a lot of work on offline reinforcement. That's a very interesting set. And again, we show the standard race it held for regularized optimization as compared to the prior work in they saw much lower rates. And also the data diversity in our case, in this linear case, is smaller than the other data coverage. So in linear case, the other data coverage translated into relative condition number, which is a very common notion of distribution shift in the we used in the offline reinforcement in linear. Okay, so that's pretty much the key results and the key highlights of this, and we position this into with the other literature. So as we have some time now, so let me just go over some maybe some key technique highlights that in this result. But before maybe I can do that, so I'm happy to like take any question if we have at this moment.
Excuse me?
If we have any questions at this point, so I'm happy to answer before I can proceed into the technique highlight.
Excuse me, can you hear me?
Yeah.
Yes, I can hear you.
Yes, I'm wondering the adaptive data collection scheme, whether it is the key point. Yes, this one. The adaptive data collection scheme, is this the key point that makes you achieve the standard rate?
So adaptive it's just a general setting of data collection, and it's not the key point. So our result holds in the more general setting, but we don't need the adaptive setting to make the result hold in our theorem.
Thank you. Then what is the key point that brings you to k to the -1/3 to the -half?
Yeah, that's a great question. So actually, if you see the algorithm framework that we presented, it basically is similar. And actually, the first two algorithm, version space and regularized optimization, is similar to the literature. The only novel algorithm is a positive sampling. But what makes us achieve this rate is purely because of analysis. So we have more refined analysis to show that actually regularized optimization achieve a standard rate rather than a slow rate, as shown in the prior. So my short answer is it's in refined analysis, not in the algorithm.
Thank you so much. So I'm indeed very excited, looking forward the later technical part. Thank you so much.
Thank you so much for your question. All right. So let me go briefly into the technical parts of this result. I just give very informal and very high level steps in this game. So basically, the key proof techniques in our analysis is combination of data diversity, decoupling argument, and some basic concentration inequality. Okay, let's get started with just the very first step that we need to do the proper error decomposition. And we care about the suboptimality. So suboptimality is of the pi hat and the comparative policy pi. Okay? So basically, we can decompose this suboptimality into three components. Right? So the first component is nothing but the Bellman error under the comparative policy pi that we want to compete against. The second component is the value gap at initial state. So this is the Q under bar is the value estimate from the algorithm, and V1 PT pi t is the one we try to compete against, because pi t getting closer to the comparative. And the third term is I don't give the detail. The third term is basically the regret from the online learning, because we employ the multiplicative Weiss algorithm. So this third term is quite standard to control. Okay, so it's scale 1/square root of t, where t is the number of iterations. So we mostly concern on the first term and the second term, the Bellman error and the value gap at initial state. So one of the key things in to obtain the result is like the decoupling lemma, which is actually okay. Let me present the decoupling lemma here. So lemma say that, okay, so on the left hand side we try to bound the Bellman error under the comparative policy pi. Okay, and we can bound it into three terms on the right, three components on the right hand side. So the first component is square Bellman error under the offline data distribution. So let me recall that mu is the behavior policy that have collected the offline data, and T is the Bellman operator. Okay? And this is Bellman error, and square error here. And the second component is the data diversity measure that we have presented, C, pi, and epsilon. Okay, 1 to over k. And the third component is basically some small additive error in extrapolation, epsilon. Epsilon we totally can control. And the thing here is that this decoupling lemma is very easy to prove. Basically, it's just simple rearrangement and using AMTM and the definition data diversity. But it's very powerful on the proof to obtain the unified result. Okay, and noted here is that the inequality holds for any lambda greater than 0. We control the lambda. And let's say let's get started with how we bound the versus algorithm roughly in a very high level. Okay, so now we want to bound the square Bellman error under the data the offline data distribution mu, okay, at the left hand side, and we can use we can use just Freeman's inequality to up about it by the empirical version, right? So we can go from the aesthetic version to empirical version here, and this is basically empirical square Bellman error. Okay, and in the inversion space, so we minimize this empirical square Bellman error over all the function that consists of the offline data, and this minimization can be up about it. I say in the standard way. Okay, so it's very standard to obtain the up about this minimization, and also the value gap term. The value gap term here basically is negative with high probability. We're using because the nature of versus Bayes algorithm is that they try to enforce the pessimism in the initial state, so it can be proved negative with high probability. And then after that, we just plug in this into the decomposition using decomposition of the suboptimality bound. Then we get this. Okay, so then we just minimize the right hand side with respect to lambda. Then we get to this rate. So 1 over square k sample capacity and the data diversity. It's simplified a lot, and it holds up to some constant, absolute constant, and in high probability. But that basically the gist of the proof. And for regularized optimization, actually we should proceed very similarly. Okay, so for regularized optimization, we should start with okay, this function, this one is just Bellman error under the comparative policy pi, and we possibly determine the value gap in the initial state. And then we use the decoupling lemma. Okay, the decoupling lemma just transfer this into the square Bellman error under offline distribution. The mu here is the offline distribution, and still we keep the same value gap as initial state. This is data diversity, some adaptive error h epsilon is accumulated over time step, and rearrange it, and then use Freeman's inequality here. Then we translate the expected error into the empirical error. So things here that this guy in the numerator here, this is exactly the regularized objective function that we try to minimize over. Okay, so this is exactly the regularized objective of regularized optimization. When we minimize all of this using standard concentration, we can basically bound this one by scale with sample with model complexity, scale with the boundedness and the horizon. That's standard step we obtain in the regularized optimization. The positive sampling thing a little bit more complicated though the general flow is similar, but it's much more complicated. But basically, the gist here is about the log partition function, which is basically the expectation of this guy. So the first one is likelihood function. Let's say the second one is the value gap, and then the log of the posterior distribution. Then we can lower about this by square Bellman error and the outlier distribution. This term, the mu here, the outlier distribution. And also the value gap term here, and some extra term that we totally have control over. And then we up about Z, the log of partition by this one. So it's scale with gamma lambda over 1 square root k, and then for the complexity. And plug it in using decoupling argument that presented earlier. So basically, the worst case regressive positive sampling here is can turn into this form, and then again we minimize is with respect to the values of lambda. Sorry. So then we get back to this rate. Okay, and again this hold up to absolute constant. Basically that's the gist of all the proof, and I don't want to go too much on detail, but just keep the high level of this, and that's it. So let me just summarize what I have in this talk. Basically, I talk about the offline reinforcement learning problems, and in this work, we particularly like providing some kind of notion of data diversity to measure distribution shift in offline reinforcement learning, which generalize the data coverage notion in the previous book. And also we provide a unified theory that show a new result that versus-based regularized optimization and process sampling extended assumptions, they are comparable in the theory about in the value optimality test. Okay, so also all the technical result paper is that we use new decoupling argument for offline RL work very well in the unified theory. And also we have a new techniques handle the data dependent on analysis, the work case, process sampling, which can directly actually apply to resolve some technical issue in some previous work using process sampling in the year 0 again. That's it. So thank you very much.
Thank you very much for Tang's great talk. Hi, audience. If you have any questions, kindly ask.
So thank you for the technical details. So I would like to know the intuition why you designed this decoupling lemma. So is it because you decouple some complex term into A plus B plus C so that it makes you easier to analyze, to refine your analysis?
Yeah, I see. Thank you for your great question. So actually, so decoupling, let's look at this one. I think the intuition can be very simple when we look backward. So here the decoupling of the lemma, basically it say that on the left hand side is the Bellman error under the comparator policy pi. Okay, so pi is the policy that we want to compete against. And now in the right hand side, we have the square Bellman errors, but under the behavior policy mu. And then we have extra term of data diversity. So basically what it says is that if you the error in the Bellman error on the left hand side have two sources. The first source is from the extrapolation because of the distribution shift, but the decoupling lemma is kind of like handle that distribution shift by this inequality. Okay, so all the distribution shift will be taken care of by this data diversity quantity. And now what we care about now is only to focus on about the square Bellman error under the outlier distribution and the mu. So the square Bellman error under mu is basically it's just the in distribution error, which might have some, like, we can leverage some standard tools to control it. So it decoupled the extrapolation error or distribution shift error, different from the in-distribution error.
I see. Thank you so much. This is very clear.
Thank you so much.
My second question is that the technique developed for the offline methods, can we apply it to the online version, or do we need a new set of tools for analyzing an online method?
I see. That's a great question. What I'm seeing is that usually, what I see usually most of the algorithmic advances have been already developed in online setting first. Okay, so even the version space I'm not sure the regular optimization, but the version space, that the version of the online learning already studied very early, and even like more positive sampling is studied like extensively for online version. But for offline, this, because of the distribution shift problems, which is quite different from the exploration problem in online setting. So the analogs of these algorithms in offline setting have not been around much. That at least I can say. And then basically, this is the result that okay, some kind of component in the online learning, it can be used to design the offline, as long as we somehow we respect the pessimism principle. Say, for example, okay, actually, if we look at in comparison with online setting, so it's very kind of mirror thing. Okay, so there are posterior sampling for online setting, but instead the pessimistic prior here, basically they have something called, you can guess, like optimistic prior. So optimistic prior, instead of using minus lambda, they're using plus lambda. Okay, so they encourage sampling of the value function that have the value maybe higher than the one that they try to estimate. But here, in offline setting, we flip a coin. We have flipped the sign of that one. So we take the minus one because we want to increase the pessimistic prior. Is it clear?
Yes. Thank you so much.
Thank you so much.
Hi Tom. I have a question. Can
Sure.
I look back at your data diversity measures?
Sure. Yeah.
So I understand there are many kind of other data diversity measures. For example, some Gini coefficients, coefficient kind of things. So you propose a measure like a chi value, right?
Yeah.
So may I know the disadvantage or advantages of your proposed measure compared to others for measuring the diversity of like the distribution?
Sure. That's a great question. So basically, okay, so the advantage is that you can think of this notion. It's basically generalized. It generalized all the previous notion. I showed somewhere in the slide. So it's always up about it. For example, it's always up about it by it's always up about it by the like relative condition number, or the single policy concentration coefficient. This measure uses lossing offline reinforcement. So this is always up about it by this time. So in some scenario, the single policy concentration coefficient can be infinity, but this data diversity can be finite. So in that scenario, that can separate the learning. And also the data diversity basically actually it comes very natural during the analysis, because we try to decompose the extrapolation error from the in-distribution error. And if we do this from first principle, actually, it's come out very natural. And it turned out that data diversity also generalized the notion of data coverage in the previous book. And another thing, another reason is data diversity is inspired by something called task diversity in transfer learning setting. So recently, there's one paper from Microsoft. They proposed the task diversity. They try to measure the transferability from one task to another, and the motivation is pretty much the same. Of course, there's some difference, but that's the same vein of motivation.
Okay. Thank you very much.
Thank you.
Yeah. All right. If there are no further questions coming up, let's thanks again for Tang's great talk today. And yeah, we also hope you can visit Tokyo in the future to visit our office at Nihonbashi, in the center of Tokyo.
That would be my pleasure. That would be my pleasure. Thank you. Thank you very much for having me, and thank you much for having this great seminar and give me an opportunity to share and talk with you about the research. And I love to have opportunity to visit at some time.
Please, yeah, please come if you when you have.
Thank you so much. Thank you so much.
Okay, next, let's welcome our next speaker, JianFu. Let me introduce JianFu to our audience. JianFu joined Shanghai Jiao Tong University as an assistant professor in February 2023. His research is focused on generated contents and trustworthy AI models. He has an impressive publication record with over 20 papers in top conferences or journals, and he holds the position of visiting scientist of Riken AIP as well. JianFu earned his PhD in computer science from Department of Computer Science and Engineering at Shanghai Jiao Tong University, China in 2020. Prior then, he received his bachelor degree in ECM honors class from Zhiyuan College, also from Shanghai Jiao Tong University. In 2015, he had been recognized with prestigious rewards such as China's National Scholarship and Nguyen-Tang Education Fund Fellowship. Let's welcome JianFu to give us his talk today. Hi, JianFu.
Thank you, Jingfeng. Thank you for having me today for this talk. And let's proceed. My topic, the topic of my representation is history and latest developments of image generation models from GAN to diffusion models. Okay, as Jingfeng has already introduced me, let me introduce myself again. I'm currently affiliated with the Qingyuan Research Institute at Shanghai Jiao Tong University and serving as a visiting scientist in the tensor learning team led by Qibin Sensei at AIP. And my primary research focus revolves around image generation, and I have contributed some works to areas such as image painting and image harmonization. So if you are interested, and you can scan the QR code here for further details on my works or send emails to me. Today, I aim to provide you with insights into the field of image generation and its recent development. Additionally, I'm also keenly interested in few shot and long tail recognition, adversarial examples, and graph neural networks. I hope to have opportunity for fruitful discussions with all of you. So let's get started. The image generation models have drawn substantial attention from academia and industry since 2014. These models leverage learned features from a data set to generate new images with similar characteristics. Among the notable models in this field are generative adversarial networks, variational autoencoder, flow-based model, and the diffusion model. Generative adversarial network operates on a min-max adversarial game principle to produce high-quality images. It consists of two networks, the generator, which transforms random noise into images, and the discriminator, responsible for distinguishing real from generated images, effectively assessing the authenticity of the generator's output. Variational autoencoder is a latent variable-based model used for image generation. It builds upon autoencoders and incorporates variational inference to learn the distribution of latent variables. Flow-based model employs reversible transformation to learn the underlying data distribution. These transformations can be reversed by their inverse functions, making the model suitable for density estimation and image generation tasks. And in recent times, the diffusion models have emerged as a novel approach for image generation. It utilizes a diffusion process where the image pixels progressively noisy, resulting in generation of new images. Okay, so throughout this presentation, we will highlight the remarkable achievements of these methods in various applications. Our main focus will be on GAN and diffusion models, as they represent the most successful image generation models to date. So first, let's introduce what is generative adversarial network, I'll say GAN. GAN have demonstrated remarkable success in various generative tasks, enabling the replication of real-world rich content, including images, human language, and music. Inspired by game theory, GAN employ a dual model framework comprising a generator and a critic. These two models engage a competitive process where they simultaneously strengthen each other. However, training GAN models can be quite challenging, as it often involves issues like training instability and convergence problems. To understand the mathematical foundation of the generative adversarial network framework and the complexity of this training process, let's discuss its two key components. The first component is the discriminator. The discriminator serves as a critic and estimates the probability that given a sample belongs to the real data set, it is optimized to distinguish between the fake and real samples accurately. The second part is generator. The generator is responsible for producing synthetic samples based on noise variable inputs. By capturing the real data distribution, the generator aims to generate samples that are indistinguishable from real ones, effectively fooling the discriminator. During the training process, the generator and the discriminator engage in a competitive min-max game. The generator endeavors to improve its sample generation to deceive the discriminator, while the discriminator strives to become more proficient at detecting fake samples. This intriguing interplay between the two models leads to mutual improvements. However, training a GAN model can be challenging, as it may encounter issues like training instability or failure to convergence. While GAN have demonstrated remarkable success in realistic image generation, the training process is not without challenges. One critical issue lies in GAN gradient descent-based training procedure, which involves two models, the generator and the discriminator, engaging in a non-cooperative game to find a Nash equilibrium. However, the independent updates of each model cost function can lead to convergence difficulties. Let's examine a simple example to better understand the challenges in finding Nash equilibrium in a non-cooperative game. Consider two players, the player 1 and player 2. The player 1 controls variable x and aims to minimize the function fx equals to xy, while player 2 constantly updates the variable y to minimize gy equals minus sy. Okay, due to the differing signs of the derivative of f and g, each subsequent gradient updates result in significant oscillations, enlarging the instability over time. As the number of iterations increases, the oscillation becomes increasingly unstable. Another critical challenge encountered in training GAN is gradient vanishing. When the discriminator achieves perfect discrimination, assigning a value of 1 to all real samples and 0 to all generated samples, the loss function L approaches to 0, resulting in no gradient updates during learning iterations. To illustrate this issue, we can conduct an experiment using DC-GAN. Initially, the DC-GAN is trained for 1, 10, and 25 epochs. Following this, the generator kept fixed, and a new discriminator is trained from scratch, and the gradients were measured using original cost function. Notably, we can observe a rapid decay in gradient norms, reaching as low as 5 orders of the magnitude after 4,000 discriminator iterations. In the best case scenario, the gradient vanishing phenomenon can present a significant hindrance in the training process, as it impedes effective learning and convergence of GAN models. Another problem is discriminator capacity. Here is a display of model learning results. The image inside the yellow box are real images, while the others are generated images. We can observe that the GAN perform exceptionally well on handwritten digits and generating high realistic effects. But however, when the data complexity increases, like from faces to many similar patterns or intricate animals and scene images, GAN performance becomes less satisfactory. The generated image gradually become blurry, failing to effectively produce specific object or scenes. Hence, training GAN faces a challenging dilemma. The first dilemma is if the discriminator performs poorly, the generator lacks accurate feedback, and the loss function fails to represent reality effectively. The second one is if the discriminator performs excellently, the gradient of the loss function approaches to 0, leading to extremely slow or even stalled learning. The dilemma significantly hinders the successful training of GAN. During the training process, GAN may also encounter a significant issue known as mode collapse, wherein the generator gets stuck in a state where it constantly produces the same outputs. Despite being able to deceive the corresponding discriminator, the generator fails to effectively learn and represent the complex real-world data distribution. As a result, it becomes confined to a limited set of samples with extremely low variety. For instance, in the case of a DC-GAN model trained with an MLP network having 4 layers, 512 units, with ReLU activation function, the lack of a strong inductive bias for image generation contributes to a noticeable degree of mode collapse, limiting the diversity of generated samples. The reason behind this phenomenon is that ensuring the realism of generated images alone is not sufficient. We also need to generate the images to align as closely as possible with the data distribution of all real samples. Let's consider a data set. Okay, let's consider a data set comprising half cats and half dogs. Sometimes the generator may produce many seemingly realistic images, but they are all generated dog images, and the generator struggles to effectively produce cat images. This is a common issue in GAN. When the generator fails to generate cat images, the discriminator's accuracy in distinguishing cats becomes nearly perfect, resulting in negligible error loss, and it becomes challenging for gradients to effectively backpropagate to the generator to help generate cat images. Okay, conversely, if the generator produces high-quality dog images, the discriminator incurs significant loss discriminating dark images, further enhancing the generator ability to produce dark images. Okay, this situation makes the problem of mode collapse even worse. So these are the training issues of GAN. And now let's talk about how to improve GAN. One notable advancement is self-attention GAN, or say SA GAN. This technique introduces attention map, enabling the generator and discriminator models to focus on specific regions of the image. The addition of an attention module to help deep convolutional model architecture is the key to the SA GAN approach. The attention module is incorporated in both the generator and discriminator, and these components are trained in an alternating manner, optimizing the hinge version of the adversarial loss function. Through the integration of attention maps, SA GAN fosters better information capture and improves the generation discrimination process, leading to a more stable and high-quality results. BGAN represents a significant advancement in the field of image generation, achieving impressive results through the integration of various best practices by effectively scaling up with both the batch size and the number of model parameters. BGAN has successfully enabled the generation of high-resolution and high-fidelity images. This model contribution lies into the thoughtful design decisions for both the architecture and training process. Progressive growing of generative adversarial network is a specialized type of GAN designed to scale the generation of high-resolution and high-fidelity images. And the fundamental approach involves training a GAN initially on very small images, such as 4x4 pixels, and progressively increasing the size of the generated images in a stepwise manner. The aim is to achieve the desired output size, such as 8x8, 16x6, 16x16, and so on, while simultaneously refining the generated content. By adopting this progressive approach, PGGAN overcomes some of the challenges faced by traditional GAN, such as mode collapse and training instability. Cell GAN is a specialized type of GAN tailored for generating high-quality images while offering precise control over the generated image cell. The core techniques employed in cell GAN is adaptive instance normalization, enabling the manipulation of image cell. So that's all about GAN. And now let's talk about diffusion models. In the context of diffusion models, we may be familiar with Markov chains. These concepts not only appear in diffusion models, but also in various other algorithms. So why do we use Markov chain? Because a key property is stationary. If probability distribution changes over time under the influence of a Markov chain, it will tend to a stationary distribution, for example, as a Gaussian distribution. With a sufficient long termination time, the probability distribution will converge to this stationary distribution. Okay, by drawing an analogy between the uneven distribution of high and low concentration to information processing, we can consider regions with high information density as high concentration areas, and the region with low information density as low concentration areas. In information processing, information can be seen as entities similar to substances, and information diffusion can be seen as movements of information entities from high density to the low density regions. Similarly, information can be seen as process of information entities disappearing due to the noise inference. Hence, the mathematical model and the physical understanding of diffusion models exhibit properties to the diffusion and information loss observed in gas molecules. Okay, by simulating the information diffusion and loss through the multiple steps of random evolution, diffusion models presents a novel and efficient approach to generate model, introducing a novel probabilistic modeling framework that describes the change in information density over time by analogy to the physical mechanisms of diffusion. In this model, information is viewed as a high-dimensional random variables that evolves over time according to specific rules, akin to the diffusion of molecules in a gas. By subjecting information to multiple steps of random evolution, the model simulates the process of information diffusion and enabling the generation of high-quality diverse samples from the distribution in high-dimensional space. Okay, in the context of data generation, diffusion models are generative models that progressively add and remove noise to learn the underlying distribution of training data. They involve two processes: the forward process, or say the diffusion process, where data is systematically noised, and the reverse process, or say the reverse diffusion process, where the noise is transformed back into a sample from the target distribution. Okay, we will explore an illustrative example of image generation using diffusion models. These models employs a unique process involving a forward diffusion and reverse stages to generate high-quality images. During the forward diffusion stage, to generate high-quality images, the input image undergoes a gradually perturbation over multiple steps. The perturbation is achieved by adding Gaussian noise to the image. As the diffusion process progresses, the image becomes increasingly perturbed, leading to a noise-rich representation. In the reverse stage, a model is trained to recover the original input data by progressively undoing the diffusion process step by step. This process allows the model to generate images with less noise, and ultimately leading to the complete reconstruction of the image manifold. Okay, the core idea of diffusion models lies in training a network capable of simulating the formation process starting from a noisy image, and the network gradually generates images with less noise, effectively reconstructing the underlying image structure. In the context of diffusion models, generating a sample through the reverse diffusion process can be significantly time-consuming, involving up to one or even a few thousand steps. According to DDPM work, it takes approximately 20 hours to sample, say, 50 kilo images of size 32 times 32 from a DDPM. Whereas again can achieve the same less than minutes on a GPU. To address this challenge, one simple and effective approach is to employ a strategic sampling schedule by taking the sampling updates every T over S steps. The process can be reduced from T to S steps, significantly improving the sampling efficiency. DDPM shows superior performance when it can afford to execute full reverse Markov diffusion steps, say 1,000 steps. However, with the introduction of DDIM, it's become possible to train the diffusion model for any arbitrary number of forward steps while sampling only from a subset of steps in the generative process. In comparison, DDPM and DDIM offers the following advantages: that the DDM generates high-quality samples using significant fewer steps, reducing the overall computational burden. And the generative process in DDIM is deterministic, meaning that multiple samples conditioned on the same latent variable exhibit similar high-level features, leading to the consistency property. And also, due to this consistency property, DDIM enables semantically meaningful interpolation in the latent variable space, allowing for smoother transitions between generated samples. Another way to make the diffusion model faster is the latent diffusion model, or say the stable diffusion. Stable diffusion represents a novel approach to image generation by running the diffusion process in the latent space rather than the pixel space. This innovation reduces training costs and enhances inference speed. The motivation behind a latent diffusion model stems from the realization that most image space contributes to perceptual details, while the semantic and conceptual composition remains intact even after aggressive compression. Latent diffusion model employs a two-step process for generative modeling. First is trims the pixel level redundancy using an autoencoder and focusing on perceptual compression. Then it manipulates and generates semantic concepts using the diffusion process on the learned latent space. The diffusion and the denoising process occur on the same latent vector, and the denoising model incorporates a time-conditioned unit augmented with a cross-attention mechanism to handle flexible conditioning information for image generation. Okay, this information may include class labels, semantic maps, or blur variants of an image. The design of latent diffusion model involves fusing representations of different modalities into the model using cross-attention mechanism. Each type of conditioning information can be associated with a domain-specific encoder, such as semantic, map, text, images, responsible for projecting the condition input into intermediate representations that can map into the cross-attention component. So that's all about diffusion models. Now let's compare GAN and diffusion models. So in order to achieve wide adoption in real-world application, generative models must meet three key requirements. The first requirement is high-quality sampling. Okay, many applications, particularly those involving user interactions, demand high-quality generation. For example, in speech generation, poor speech quality can be challenging to comprehend. Similarly, in image generation, the desired output should be visually indistinguishable from natural images. Another property is the mode converge and sample diversity. A good generative model should be successfully capture the complex and diverse nature of the training data without compromising generation quality. It is crucial to faithfully represent the data diversity to avoid overlooking minority modes in the data distribution and reduce any desired biases in the learned models. The third property is fast and computationally inexpensive sampling. Many attractive applications require rapid generation, such as real-time image editing. Reducing computational complexity and sampling time not only enables real-time applications, but also reduce the environmental impact of running resource-intensive deep neural networks that underlie generative models. Well, most current methods in generative models focus on high-quality image generation. Addressing this second and third requirements is equally important. Okay, diffusion model have emerged a promising approach, but there comes a significant drawback. Generating images with diffusion models takes significantly longer than GAN. For instance, the GAN can generate 4,000 images in about 2 minutes, while the diffusion models require 2 days for the same task. It takes more than 1,000 times for diffusion models to generate images than GAN. And it is also possible to treat runtime and image quality with diffusion models by using fewer diffusion steps and employing techniques like DDIM, but still diffusion model is much slower than GAN. One significant difference between GAN and diffusion models lie in their respective loss functions. The diffusion models utilize a pointwise loss, which may sometimes deviate from the data manifold, leading to the generation of blurry images. In contrast, GAN employs a distribution matching loss, which enables them to better adhere to the data manifolds, resulting in clearer images. However, distribution matching approach often faces challenges such as mode collapse, where certain small distributions are lost during the generation process. On the other hand, diffusion models do not encounter mode collapse due to their multi-step denoising process, which allows them to maintain diversity and generate a wide range of images. The pointwise loss used in diffusion models can be employed for initialization or correction purposes, contributing to their stability during the training. Okay, to summarize, GAN tend to produce clearer images, but may face mode collapse and limited diversity. And diffusion models maintain diversity and do not suffer from mode collapse, resulting in better clarity compared to methods like VAE that use point loss. Due to the challenges posed by loss functions in GAN, they often necessitate separate training for different conditions and datasets. In contrast, diffusion models can be trained on large-scale datasets, allowing them to adapt to various scenarios effectively. For example, the stable diffusion model underwent training using an image caption pair sourced from Line 5B, a public available dataset derived from common crawl data collected from the web. This extensive dataset contains 5 billion image text pairs categorized based on the language and filtered into separate subsets according to resolution, like of containing watermarks and aesthetic score. The training process for the stable diffusion model utilized 3 subsets of Line 5B. Initially, the model was trained on the high-resolution subsets. As training progressed, low-resolution images and those with watermark probability greater than 80% were introduced. Moreover, during the final stages of training, 10% of task conditioning was removed to enhance the performance. The ability of diffusion models to be trained at large-scale datasets enables stable diffusion models to adapt to various scenarios and tasks. Like GAN, which often require distinct models for different data domains, for example, like faces and animals and landscapes, diffusion models can use a unified model to handle diverse scenarios effectively. So that's the main difference between GAN and diffusion models. Next, we will discuss about another important property is the controllability. Okay, controllability is a critical ability of generative models. In image generation, it refers to the ability to effectively control the intervene in the generated results during the generation process. In image generation models, we aim to guide the model to produce samples that align with specific conditions or parameters. This controllability allows us to generate data targeted towards specific categories, styles, or features, or attributes. Having a high controllable image generation model enables the generation of diverse samples by varying different conditions rather than producing random samples alone. This controllability is crucial for various tasks and applications, such as data augmentation, where we can use image generation model to augment data, thereby increasing the diversity and quantity of data samples. Moreover, controllable image generation model can offer the ability to disentangle factors and assemble them to generate new samples with desired attributes. For instance, we can disentangle factors like hair color and use them to create new images with specific hair colors. Additionally, specific matching and autoregressive mechanism or modules can be designed to enhance the image quality, leading to better generated samples. In the context of both scan and diffusion models nowadays, controllabilities have become a crucial aspect, and the key elements enabling this controllability is the use of CLIP. CLIP stands for the Contrastive Language Image Pre-training, and it is a multimodal model based on the contrastive learning. The training data of CLIP consists of pairs of text and images, where each image is paired with a corresponding textual description. Through contrastive learning, the CLIP model learns to establish meaningful relationships between text and images. CLIP comprises two main components, the text encoder and the image encoder. The text encoder is responsible for extracting features from textual descriptions and can employ commonly used text transformers models to the field of NLP. On the other hand, the image encoder is tasked with extracting features from images and can be implemented using well-known CNN models for our vision transformers. But leveraging CLIP, generative models can significantly enhance their controllability. The reason lies in the CLIP's abilities to map both visual and textual inputs into a unified representation space. This representation space is enriched with strong semantic information, allowing it to facilitate various downstream tasks that involves multiple modalities. Okay, in Stable Diffusion, CLIP is utilized to convert the textual information into numerical representations, capturing the underlying intent of the text. This part provides a brief introduction to CLIP, and further details will be explored later in the feature representation. The text understanding component, also known as a text encoder, is specialized transformer language model specify the text encoder of the CLIP model. It produces a list of feature vectors, and each word token in the text mapped to a corresponding vector representation. These text features are then used as input to the image generator, which consists of several components. If you use a text like a photograph of an astronaut riding a horse, the result would look like this. Also, GAN can use CLIP to enhance the controllability. StyleGAN is an innovative image editing method that integrates the capability of StyleGAN and CLIP, enabling image modification and processing based solely on images and textual descriptors. It utilizes latent optimization, latent matter, and the global direction. The combination of StyleGAN and CLIP in StyleClip offers exciting possibilities for image editing driven by natural language descriptions. By leveraging these approaches, user can achieve sophisticated and targeted image manipulation like this with ease and precision. Another approach for diffusion model to increase the controllability is the DreamBoot. DreamBoot is an innovative model designed specifically to enhance the text-to-image diffusion model's outputs or create entirely new images. Its unique capabilities set it apart from other diffusion models, offering the personalized and contextually diverse image generation. One of the DreamBoot's key strengths lies in the ability to personalize personalized output of text to image diffusion models and user-provided images. By inputting a small set of images, usually say three to 5 images, DreamBoost generates personalized images based on the subject, each with distinct context. This is achieved through the integration of Stable Diffusion. The DreamBoost begins by feeding the images and associating a unified identifier with the subject. During the inference, this unique identifier is used to synthesize the subject in various contexts, resulting in high personalized and contextually rich image results. To achieve this personalized image generation, DreamBoost fine-tunes a text-to-image diffusion model using the input images and corresponding text prompts. Additionally, a specific class-specific prior preservation loss is applied. Leveraging the model's semantic knowledge of the subject class, this encourages the model to generate diverse instances belong to the subject class when the provided class names in text prompts, for example, like a dog. DreamBoost utilizes autogeneous class-specific prior preservation laws that promotes diversity and mitigates the language drift. Essentially, DreamBoost supervises the model with its own generated samples to retain the prior information during filter and fine-tuning. This enables the model to generate diverse images of the class prior while retaining knowledge about the class prior that can be used in conjunction with knowledge about the subject instance. During our practical experimental setting with DreamBoost, we encountered challenges where the model sometimes struggled to generate scenes and poses based on the provided text prompts. For instance, when we input 5 images of the same dog, request the generation of image depicting like a dog playing in the water or a dog is playing with a sandbox. DreamBoost predominantly generated images similar to the input data, failing to adapt to our specific text prompts effectively. So to address this challenge, we made important modifications to DreamBoost's class-specific prior preservation laws. Instead of using simple prompts like a dog, we carefully select approximately 200 distinct and detailed scene descriptions to replace the original prompts. This adjustment allows us to constrain the space of class images from large area, say the gray area, to smaller, more precise region like the green areas, thereby reducing the difficulty of learning the class-specific prior and generate faithful images aligned with the text prompts. As a result of this approach, we observe that a significant improvement in the diversity of generated images and their adherence to the provided text prompts. With a revised training approach, we can now generate customized images based on the specific input scenes, such as a dog playing in the water, or the dog is playing with a sandbox. This enhancement enables the DreamBoost to better align its image generation process with user-defined text prompts, resulting in more contextually relevant and personalized outputs. Except for the text conditions, image condition can be also considered in image generation tasks. For instance, image painting walls utilizing the background pixels. In GAN models, the focus is often on decomposing the image into different representation branches, the structural representation branch and the texture representation branch. Subsequently, multiple fusion processes are explored to achieve harmonious and visually appealing results. Let me now introduce 3 other works related to this approach. The first approach is to enhance the overall structural representation of the image. We have adopted the concept of priority filling from traditional image processing methods. As shown in the diagram on the left, we prioritize filling the red region, followed by considering the yellow surrounding pixels, resulting in higher confidence. Additionally, it is often found that edge regions of the image where the structural information is stronger. By incorporating this priority filling, we can effectively restore previously challenging cases. Another approach is to combine structural and textual information of the image. We decompose the network into different stages, and where at the end of each stage, we perform fusion between high resolution and low resolution representations. This approach leads to a more subtle and higher quality restoration. Based on the deviations, we perform feature fusion, effectively aligning the structural and texture information, thus improving the overall quality of the generated images. By incorporating these techniques, we achieve a better integration of structural and texture representations, resulting in more harmonious and visually appealing image generation outcomes. For diffusion models, how to keep the image condition controllability, the solution is ControlNet. ControlNet is a controllable image generation method based on the Stable Diffusion model. It enables image editing through in addition of conditional controls, such as canny edge maps, depth maps, and etc. The approach involves creating a duplicate of the Stable Diffusion model's UNet encoder and training only this duplicated part, while keeping the original UNet weights frozen. During the training, the conditions are converted into images and fed into the duplicated encoder. The outputs of each block in the encounter are accumulated into corresponding layers of the original UNet decoder. However, this accumulation is not straightforward sum. Instead, it employs a zero convolution before the accumulation. The term zero convolution comes from the fact that the initial weights of this convolution are set to be zero. As a result, the initial stage of the training, the additional UNet encoder does not affect the generation of the original Stable Diffusion. ControlNet offers several advantages. The first advantage is that ControlNet can be directly applied to existing Stable Diffusion models without modifying the original model. And the second advantage is that ControlNet supports multiple conditions, such as human body pose, canny edge maps, depth maps, and etc. In practice, in general, we found that GAN offers higher controllability but lower fidelity, whereas diffusion models provide higher quality but may not faithfully adhere to the input condition. Here we will introduce our recent works, compare the GAN and the diffusion model and how to combine GAN models and diffusion models. To achieve controllability, we integrate both GAN and diffusion models in our work on the virtual try-on task. Okay, virtual try-on task is a crucial image synthesis task that the goal is to transfer clothing from one image to another while preserving both the human and clothing details. While many existing methods rely on, again, on this task, they employ an implicit a warping module that aligns the target clothes with the human body. However, the reliability of such a framework is heavily contingent on the quality of work garments. Work garments in low quality impede faithful generations. The diffusion models have emerged a promising alternative for generating high quality images in various applications. However, solely using clothing as a condition to get the diffuser model in painting is insufficient to maintain the close details accurately. So here we combine the diffuser model and GAN models for more accurate virtual try-on performance. To address this challenge, we propose an exemplar-based in-painting approach that incorporates a warping module to effectively guide the diffuser model's generation process. The warping module performs initial processing on the closing, preserving local closing details effectively. We then combine the warp closing with the closing agnostic person image and introduce noise as an input for diffuser model. Additionally, the warp closing also serve as local conditions for each denoising step, ensuring the output retains as much details as possible. Our approach successfully harnessed the capabilities of the diffuser model, and the inclusion of the warping module significantly improves the quality and realism of virtual try-on results. Okay, by combining the GAN and diffuser models, we have deployed a powerful framework for achieving better controllability in the virtual try-on task, leading to high quality and visually pleasing results. So that's about the one important property of controllability in image generation. Finally, we will talk about the evaluation metrics for image generation. Assessing the quality of generated images can be a challenging task. While manual inspection is one approach, it is subjective and time-consuming. To address these challenges, researchers have developed many measures to evaluate performance of image generation models. Two popular metrics used for evaluating generated images are inception score and Freiheit inception distance, FID. These metrics provide quantitative assessment of the generated image's quality and can be complemented with qualitative evaluation to achieve more comprehensive evaluation of image generative models. However, evaluating generated images still poses difficulties due to the lack of objective measures. Here, I will present our latest research on evaluating image in painting using pre-trained image in painting models. The image in painting problem is inherently ill-posed, making it challenging to establish reliable evaluation metrics. Existing evaluation involves direct comparison between the similarity between the pairwise original and the restored images, either in the pixel space or embedded feature space like FID and inception score. However, these metrics require access to the ground truth images, which may not be available in practical scenarios. Therefore, there is a need for a metric that can solely rely on the in-painted images themselves. Another concern is the potential bias introduced by these metrics. In real-world images, the mask area representing the corrupt region can cover a significant portion, making it difficult to accurately predict the content concealed by the mask. Additionally, the content within the crop region may have multiple plausible solutions. For example, in an image with a mask rock, there could be several acceptable outcomes for height and patterns of the rock, as these images have shown. As a result, directly using ground truth images for evaluation can lead to unfairness and biased assessments of in-painting methods. Here we show two different types of masks, the normal mask and the patch mask. Normal masks obscure the connected region in the image, resembling the brush-like or box-like shapes. On the other hand, the patch mask independently determine whether the mask, each patch, resulting in isolated small regions of blocked images. When we use normal mask, for inpainting, the resulting images exhibit significant variance and can deviate substantially from the original image. Conversely, when we employ patch masks, the inpainted images prioritize preserving visual and a low-level semantic consistency while maintaining the structural and high-level semantic context of the original image. As a result, the inpainted images display low variance and closely resemble to the original image. So based on the observation we mentioned before, we have devised a comprehensive evaluation framework. Our approach utilizes a multi-path strategy to enhance self-consistency by iteratively re-inpainting the inpainted images with multiple patch masks. This iterative process enables us to calculate the perceptual metric between the inpainted images and their corresponding re-inpainted versions, effectively capturing the consistency and fidelity of the inpainting method. Unlike conventional evaluation methods that rely solely on pixel or feature space similarity with the original images, our proposed approach emphasizes intrinsic self-consistency. This empowers us to explore diverse and viable inpainting solutions while mitigating the potential biases. By adopting this evaluation framework, we can gain deeper insights into the performance and capabilities of the painting method, provide a more robust and comprehensive assessment of its effectiveness in image generation tasks. So that's all about my talk today. So in summary, we have introduced the GAN and diffusion models, followed by a comparison of their respective advantages and limitations. GAN offer faster inference but require more effort in training. However, GAN have limitations in large-scale training, restricting their adaptability to diverse scenarios. Therefore, GAN might not fully adapt to specific task data unless they are well-trained. On the other hand, diffusion model excel in large-scale training and demonstrates superior cross-domain adaptability, resulting in generation of high-quality images. To achieve practical applications, we recommend fine-tuning and retraining based on the pre-trained diffusion models. In their performance falls short of expectations, GAN can be utilized further training to meet one or more demanding requirements. Additionally, for data types like videos, multi-channel, hyperspectral images, medical images, for etc., where the large-scale data sets are not available, GAN are a preferable choice over diffusion models, which lose their advantages in large-scale training. GAN and diffusion models each offer unique advantages and well-suited for different use cases. In general, GAN offer higher controllability but lower fidelity, whereas diffusion models provide higher quality but may not faithfully adhere to the input condition. By combining their strengths and utilizing controllable generation methods, we can achieve more versatile and robust image generation. Currently, we still lack of effective way to assess the authenticity of the generated images. It remains challenging to devise a comprehensive and reliable evaluation method for assessing the realism of generated images. One potential approach could involve designing evaluation metrics based on the training process is to evaluate the quality image generation is to utilize the pre-trained models. So that's all about my today's talk. Thank you. If you have any questions, please.
Thank you very much for JianFu's great talk.
Yeah.
Hi, audience. Do you have any questions? Feel free to ask here. Before that, I do have questions on your personalized modifications kind of things. Can you go back to your slides too? So I think that this is the work still in progress.
Yeah.
It's a faithful personalized image generalization.
Yes.
So my question is, how do you define the personalization? What kind of personalization do you think is more could be the future future research directions?
The personalized here is defined as the user will input some specific images, just like in this figure, the user will input a dog. Say maybe this user input this dog, maybe another user will input another dog, or say a specific cat. And the personalized defined here is to generate the corresponding images to the input. Say like if this user input this dog, and we will generate images based on this dog. If the user input another dog, and we will generate images based on another dog. So that's why faithful is very important, because if we the user input dog A and we generate a dog B, then we fail to generate personalized images.
I see. So a follow-up question is, would this process is a few shot learning or something is it require a lot? Please.
Yes, it's related to few shot learning. It's kind of similar to the few shot recognition, or say classification in machine learning. Is called few shot generation, that you input a small amount of, say, a few images, and we can generate more images based on your input.
I see. So for example, during this process, do we have to slightly change the weight of the pre-trained model?
Yes, we need to fine-tune, or say slightly train update the pre-trained models.
Slightly, right?
Yeah.
I see. Okay. No, thank you very much.
You.
I have no further questions for this. Yeah. All right. If it's no further questions, I think you can also ask JianFu if you
hello, may I ask a question?
Yes, please.
Sure. Yeah.
Hello. So I'm very interested in your the talk, and I find it's very useful. So I'm wondering, have you considered any application on the medical? Have you considered any medical application with your method? Because diversity and faithfulness is especially important in the medical things, because we couldn't it's not like dog and cat. If the if the symptom is not face, then it will cause a very big problem. So I'm wondering, do you have any exploration or consideration on this field?
Yeah, that's a very great question. You mean you want to say apply the personalized generation in medical images, right?
Exactly.
Yeah. Okay. So my opinion is that if you want to apply image generation in medical images, you can choose generative adversarial network like GAN. But if you want to use diffusion models, is most of the time is needs more data to train. So for medical images, it seems like there are not sufficient amounts of training data. So I think you can try stable diffusion, any diffusion models, and you can see if it can fit the medical images, like it can generate any reasonable or say plausible images. If it fails, you have to train again to fit your requirements.
Okay, thank you.
Thank you. We can discuss later if you have. Okay.
Sure.
I also have a follow-up questions by Lee. I think in medical domain, usually the medical images are very few. We cannot train from scratch train the model using the purely medical image.
Yes.
So the question would be, could we use some pre-trained model that's trained from the public data set and can
Yes.
easily use a few short learning or fine tuning to that help the medical domains. What do you think?
Yes. Yes, it's a common approach to transfer the pre-trained models knowledge to specific small domain images such as medical images. But I'm not sure whether it can work because maybe the fidelity or say the quality of the generated medical images is very poor. So if it cannot generate reasonable images, maybe we still need to train GAN. And there are some specific approach to train GAN on a small scale data sets such as PatchGAN, or you can use some specific augmentation techniques to increase the amount of the medical images. So that's my opinion.
Sorry, if I can make a follow-up question. So how about like
Yeah,
use GAN to generate a lot of like the medical images and use that generated one to train the diffusion model?
It's also possible. It's also possible, but
will
you
it
may
have
need to
the-
generate.
But will it have the
you-
poison issue? For example, in the large language model, if you train the things on the generated ones, then actually the model
Yes.
will collapse. So will this also
Yes.
have in the diffusion model?
Yes, it is possible. You can generate more data. You can train a diffusion model based on the generated data, but you have to check the quality of your generated images. As you say that maybe your generated images are with low quality, maybe poison to train the diffusion models. So it's kind of technical. It's depends on your practice data.
Okay, thank you.
Thank you.
All right. Then thank you very much for JianFu's great talk.
Thank you.
And audience, you can also email JianFu for your further questions. Then, yeah, let's thanks again for JianFu.
Thank you.
I hope you can visit Japan.
Yeah.
In
I
the
also
future.
hope to go back to Rican
Sure.
one
We will
day.
have- Yes. All right. This is the end of today's seminar. Bye-bye.
See you.